Hello and welcome to the video for lesson 4.1. We are going to learn about inverse functions, and we're going to learn how to define one, how to verify that two functions are inverses of each other, and how to define a one-to-one function. So just kind of introducing the topic of inverse. Over the course of your life, you have learned that addition and subtraction are inverse operations of each other. And multiplication and division are inverse operations of each other. And you've learned that square root is an inverse operation of x squared, which we can take that to another level and say the nth root is the same as x to the n. So we've been learning these inverse operations. So inverse functions are in a similar thinking of how can we undo this function. It's similar to what we do when we think about how can we undo this operation. Okay, so let's define inverse functions. It says let f be a function. Remember, a function is when every x only goes to one y. A function g is said to be the inverse function of f if the domain of g is equal to the range of f, and for every x in the domain of f and every y in the domain of g. Okay, so g of y equals x if and only if f of x equals y. So this notation is f to the -1 for the inverse. Okay, and so it does not mean 1 over f. It's not like 2 to the -1 means 1 over 2. This does not mean this. F to the -1 does not mean 1 over f. Okay. And how we can prove that two functions are inverses of each other is if f is a function with an inverse f to the 1, then for every x in the domain of f, you can use the composition to prove that that they are inverses. Because if you compose f with its inverse, you get x. And if you compose its inverse with f, you get x. And we're going to show that. So example 1 says, verify that the following functions are inverses of each other. So if we compose f with g, we're going to take 3 times something minus 4. And we're going to put the g function in here. And then you're going to have to show this in your homework. You need to show where you're distributing this through. You can't just say, yep, it works. So you need to show that this gets distributed. Just like when we have divisions the first time. The 3's cancel and we have x plus 4 minus 4 equals x. So f composed with g has to equal x. And likewise, g composed with f also has to equal x. So if we start with the g function, and in for x, we put the function f of x. So this, because we have like denominators, we can add the numerators. And those cancel, and we have 3x over 3, which cancels, and we have x. So thus we can say that f of x and g of x are inverses of each other. Also, a unique thing is that if they're inverses of each other, they are inverses around this y equals x line. Okay. So I'll show you that in Desmos before we move to the next example. So here is y equals 3x minus 4. Here is the g function in red. And here is the y equals x. So if they're inverses of each other, they will be symmetric with respect to that line, y equals x, and they are. Symmetric meaning half of the red line, it's cut in half there, and half of the blue line. Okay, so let's go back to our paper here. So that's how we prove if two functions are inverses. But what if I said, how do I take one equation and actually find the inverse? There's a step-by-step process that we're going to use here. And what we do is we start with the expression of the given function, and then we're just going to replace f of x with y. So y equals a negative 2x plus 3. Then we're going to leave those there, but we're going to just interchange y and x. So same equation, but x will get replaced with y and y will get replaced with x. Then you're going to solve for y. And now you have the inverse function of x. Okay, so let's do that here with this function. We have the f of x function of 4x minus 5. And we also have to check that it's the inverse. Okay, so I've got my function there. I'm going to write it as y equals 4x minus 5. That's my second step. So there's my step 1. There's my step 2. My step 3 says I'm just interchanging x and y. So now it's x equals 4y minus 5. And now my step 4 says to solve for y. So to do that, I'm adding 5 to both sides. So I have x plus 5 equals 4y. And then I'm dividing by 4. So x plus 5 divided by 4 equals y, which is my inverse function of f. Okay. And now, to prove that it's the inverse, if I take the composition of f of x composed with g of x, that should equal f. So f of x is f 4 times something minus 5, and that something is x plus 5 over 4. And my 4's cancel, and I have x plus 5 minus 5, and those cancel, and I have x. And then likewise, g of x composed with f of x will be the same. So my inverse function, I should say, it's f of inverse of f of x, and then this is the inverse composed with f. So the inverse is something plus 5 over 4, and that something is the first function of 4x minus 5. Those cancel, and I have 4x over 4, and that cancels, and I have x. So indeed, the inverse function of 4x minus 5 is x plus 5 divided by 4. Okay. Now, one-to-one functions. One-to-one functions, for a function f to have an inverse function, f must be a one-to-one function. So that means that every a that goes into f has an exact f of b. So before we were looking at the, let's say we have a quadratic here of some sort, okay? Before we were looking at just a vertical line test to prove it was a function. And so this is a function, quadratic, but for it to have an inverse, right? It has to be a one-to-one function. Okay. And so every f of a can only go to one f of b. So I'm going to show you an example here. So it says show that the function f4 minus 4x minus 6 is 1-to-1. So to show that 4x minus 6 is 1-to-1, we could graph it. And because it's linear, we can graph it fairly easy. So I could say that my y-intercept here is, here's a -6, and then it's growing by over 1 and up 4. So it's growing over 1 kind of quickly here. Okay. So to show that a function is 1-to-1, it has to pass the vertical line test, with which we know all lines do. And so did this quadratic here, but it also has to pass what is called the horizontal line test. And that says, if we do infinitely many horizontal lines, do they only go through one point? So every linear equation does pass a horizontal line test. But if we go over here to the quadratic, it does not pass the horizontal line test. So even though it's a function, it's not 1-to-1. Okay, so a linear equation is a function and has an inverse because it's 1-to-1. A quadratic equation is not 1-to-1. Okay. You'll have to, you're going to gain a better understanding just by working on these on your own, really. Graph the function f of x is 3x minus 2 and its inverse on the same set of axes using the same scale for both axes. And what do you observe? So let's go to Desmos to do that. And I'm going to just turn these off. And y equals 3x minus 2. And then y equals 1/3 plus x, 1/3 x plus 2/3. And you can see they are symmetric about the line of y equals x. So I'm going to just change the color of this here to a different color. Red. Okay. So these two lines are symmetric around the line y equals x. And that's how we prove visually that they are inverses of each other. Okay. So the reason we're learning this here in this chapter is because it feels kind of like we just jumped from quadratics and polynomials to this new thing. And it's the reason we have two inverse functions in here is because we're going to learn about two inverse functions in the rest of this chapter. So it's important that we understand an inverse and how to find it. So similar to when we looked at rational functions, we had to be aware of any inputs that could possibly make the denominator equal to 0, which would cause the function to be undefined. We have to do the same here. I should say possibly. So if we are taking an even root, the radicand has to be greater than 0, or we will have an undefined function, because we can't have the square root, right? The square root of a -2. We know that then we come up with imaginary numbers. So we have to have only things that are greater than 0 underneath the root if there is for an even root. So it's just so that the function f of x equals x to the 4th when x is greater than or equal to 0 has an inverse, and find the inverse. So we're restricting that value only to when x is greater than 0. Otherwise, it's going to be the issue that we have here with this quadratic. It doesn't pass the vertical line or the horizontal line test. Okay, so we are going to write this as y equals x to the 4th. And then we're going to write them like this. And then to undo this 4th, we're taking the 4th root. And so the 4th root of x equals y, and that is the inverse as long as x is greater than or equal to 0. Okay, so let's just go to Desmos so we can check these out. So we're going to just turn off these, and we're going to put in y equals x to the fourth. There's that equation. And we're going to really only look at the right-hand side because we only want x's that are positive. And then y equals, and to do the fourth root, we're going to have to do our menu here. And we're going to have to go into our functions. And it looks like it doesn't, we're going to have to write it. Oh, there it is, the nth root. And that is going to be the fourth root of x. Okay. And you can see that if we only look at when x is positive, they are symmetric around the y equals x line. Okay. And then looking at an application here, it says find a function c of x, which takes the number of inches as an input and produces the number of centimeters as an output. Also find n of x, the inverse of c of x. So c of x takes the number of inches, so inches as an input, and produces a number of centimeters. So we have to look up how many inches are in a centimeter. And you can research that on your phone if you'd like. Okay. So 0.394 inches is 1 centimeter. Now, we could also, if we go to Desmos, I'm just going to turn those off. And I take 0.394. I'm going to hit this fraction bar, the fraction button, and see if it will turn it to a fraction. Okay. So that fraction is also 197 over 500. 197 over 500. That's just another way we can write it. So let's go to our paper here. So these are the same. And so if we want to find the inverse, which is n of x, then we're going to divide. We're going to call this y and then rewrite it as x is 0.394 y. And then we're going to divide by 0.394. And that is going to be the inverse of c of x, or it's n of x. Or what we could end up doing then, right, is just say 500x over 197 equals y, or n of x. And that goes, so essentially, this goes inches to centimeters, and this is centimeters to inches. And then let's write that as a fraction. Let's go to Desmos here. And we'll write it as 500 divided by 197 is 2.53, 2.54. So 2.54, if you do 1 divided by 2.54, that's how you would get that 0.394. So 1.254. So it's 2.54 centimeters is equal to 1 inch. Is equal to 1 inch. Very cool. So now we know how to go from a function to its inverse. We know how to tell if a function has an inverse, and we know how to prove if two functions are inverses of one another. Catch me back for another lesson.